Hello and welcome to part 7 of my read and work through of Generating Functionology by Herbert Wilf. Last time we were looking at the Stirling numbers of the second kind, which were, we had the notation n curly brackets k, which was a number of ways to partition n objects into k classes, and we found a formula for nk in curly brackets by considering the generating function bkx, which is a sum from n equals 0 to infinity of nk in curly brackets x to the n. And considering this, we were able to find a formula, a bit of a big messy formula, but still looks quite a nice formula nonetheless, for n and k in curly brackets. And there was a couple of things that I wanted to have another look at after I'd finished that video, because I went through the calculation of that formula quite quickly, and I just wanted to get through the calculation, and there was a thing that I didn't really think about, and the thing is that they'd extended, so this combinatorial definition here makes intuitive sense for n and k greater than or equal to 0. The only one that could cause a slight amount of difficulty here is 0, 0. And it makes, if you think about it though, it does make combinatorial sense for this to be equal to 1, because you're asking how many ways are there to partition n objects into k classes. Well, so you're basically looking at partitions of the empty set into k classes, and what's a collection of k classes? Well, it's a collection of, it's a set of sets, in other words. So if we had k classes, a set of, so say, you know, we were looking at 5, and this was our set of 5 elements, and we wanted to split it into k classes. Well, we could write that as a set of sets, and say I wanted to split it into 3 different things. It might look something like this. We might have 1, 2, 3 in there, and 4 and 5 in those two. So what would it mean for k to be 0? Well, it would mean the number of sets within this set of sets is 0. So it would mean that the set of sets itself was the empty set. Now, if that makes sense, that can only happen only in the case where we're looking at n equals to 0. So the number of ways to partition the empty set into 0 classes is just 1, and it's the collection of the empty set of classes. Nothing at all. So this is the only time. It's a bit hard, but if you think about it, it makes sense. So we had a very natural definition for n k curly brackets for n and k greater than or equal to 0, and thinking about the combinatorics of it, we had the following recurrence relation. I think this was it. N and k in curly brackets is equal to n minus 1 k minus 1 plus k, and it was n minus 1k, wasn't it? Let me just see if that was right, if I can find that in the book, which I've got that right. Yeah, I have 1.6.3. And this will make combinatorial sense for n and k greater than or equal to 1, because we have an n minus 1 and a k minus 1 cropping up in this recurrence relation, and so if these were n and k were 0, then we'd have to be considering minus 1, and that doesn't make much combinatorial sense. So if we could only consider this for n and k greater than or equal to 1, but what the author did was to extend it to all n and k, negative and positive, any integers n and k, and in doing so he introduced an exception for when n and k were both 0, which I thought was strange. It gives you a lot to think about. You have when you're using your recurrence relation in your generating functions, you have to be thinking, oh, well, am I accidentally using this exception that I'm not supposed to be using? So, and when that came up was when we were calculating this BK, and so there's trade-off in both ways. So if we carry on with the classical way, where we sum from n equals 0 to infinity, we have to worry about the indices of our sum. But if instead we just sum over everything, and we sum from n equals infinity to plus infinity, and have that these are 0 for when n is negative, then we don't have to worry about our indices anymore. However, we have a trade-off in the other direction. We have to worry about, is that exception coming up for when we're using the recurrence relation for n and k is 0. But it turned out that in the computation of bkx, the computation of the recurrence relation for bkx, but that would never have come up in the way we did it. So I'll just quickly recap that. So if we have that bkx, we'll just write it out again. I'm going to say from minus infinity to infinity. I'll write it out to be explicit. This is exactly what we did in the book. X to the n. And so what we do is we take this equation here and multiply both sides by x to the n. And we sum over all n for which the recurrence relation is valid. Well, we've extended this to all n and k, all n and k integers, but nk is not equal to 0, 0. So we didn't use that case. But provided that we take k to be bigger than 1 or greater than or equal to 1, we're never going to come up with this. So let k be greater than or equal to 1. And then we can just sum this over all of the integers n, and it works exactly the way it did in the book, and there's no problems because k is always greater than or equal to 1, and what we would get is on the left we'd get b. So I'll just write this out again. So you'd have sum from of all n x to the n nk, and this is just bkx. Then going to have this next term, so it's equal to the sum of x to the n minus 1 k minus 1. Well, we have an n plus 1 here and an n here, so what I'm going to do is I'm going to make these the same, change that to an n minus 1 and take an x out. But because we're summing over all n an integer, we can shift it by 1, so I can just change this to an n, not to an n. So this bit is x b k minus 1 x, and then the last term is k sum x to the n minus 1 k, and we could do the same again. We could take an x out and change that to n minus 1, and then shift everything again because we're summing over all of the integers, and that just becomes an n, and this becomes plus k x b k minus 1. So, and then we got that, and rearranging that, we got our recurrence relation bkx is equal to x bk minus 1x over 1 minus kx, and that's how we got that. And so, but all the time I was doing that, I wasn't quite comfortable that I wasn't missing something, and I was uncomfortable with the fact that I hadn't checked that I wasn't hitting this exception in a recurrence relation. But providing that we're assuming k is greater than or equal to 1, it works fine. So there's nothing really to worry about there. But as I say, it's a trade-off, and I think I kind of prefer just being careful with the indices. So instead, we would take this and we would sum from n equals 1 to infinity instead of over all n, and then we would just be careful with our indices, and it would end up coming out exactly the same. So I just wanted to mention that. So if we continue reading where we left off, then the last thing that we had was, it pointed out, it said, at the same time, note that the formula says that n2, curly brackets, equals 2 to the n minus 1 minus 1. Can you give an independent proof of that fact? So I'm just going to think about that for a second. So what was our formula? Our formula was nk, curly brackets, is equal to the sum from r is 1 to k, minus 1 to the k minus r to the n, over r factorial, k minus r factorial, for n, k greater than or equal to 0. So what if k is 2? So n2 is a sum from r equals 1 to 2, minus 1. So k is 2, 2 minus r to the n, over r factorial 2 minus r factorial. So we've only got two terms in this sum to worry about, so it starts with r equal to 1. So 2 minus 1 is 1, so minus 1 to the 1, 1 to the n, over 1 factorial, times 2 minus 1 factorial is again 1 factorial, plus, so r is 2, so minus 1 to the 0, it's 2 to the n over 2 factorial times 2 minus 2 factorial, which is 0 factorial, which is 1. So you get here, this bit is minus 1 plus, and this is 2 to the n over 2, so 2 to the n minus 1. So that's what the formula tells us, and the book asks us, can you give an independent proof of that fact? So let's have a little think about that. So, number of ways to split the set from 1 to n, set of n objects, into two subsets, two disjoint subsets, and they have to both be non-empty because, yeah, two non-empty subsets. Well, if we just think there are 2 to the n subsets of n, square brackets n, which is that set there. There's 2 to the n subsets because there are n objects, and each, for every, you can choose whether each element of this set is either in or not in a subset. So that gives you two choices for each of them. They're all independent of each other. There's 2 to the n possibilities. So 2 to the n subsets of n. So how many of these subsets are, well, before I think about that, so say S is a subset of 1 to n. Then, providing that S is not equal to the empty set and s is not equal to the whole set, then if t is equal to the complement, so all of those elements from 1 to n which don't belong in S, then also t is non-empty and st are disjoint, and their union is equal to the whole set. So this is going to give us every possible partition of 1 to n into two classes. And the reason that is because if we have a partition of 1 to n in two classes, then take one of those classes, and it is a subset of the set 1 to n, and call it S, and it has a complement, and the other class has to be the complement because it's all the rest of them. So it occurs as one of these. However, the problem here is that every time we're doing this, we're counting 2 for every time we're doing this. So every time we choose a subset S, and then we take the complement to get the set split into two classes, we could have instead taken S to be the complement T. And so there's two ways that we can go about getting each partition of n into two classes. So the number of ways there are to pick a subset S which is not empty and is not the whole set, which is 2 to the n minus the 2 that we don't want, the empty set and the whole set. That is twice the amount that we want. So the amount we want is 2 to the n minus, so 2 to the n over 2, which is 2 to the n minus 1, minus 1. So it makes sense. It's easy to prove independently as well. Moving on. Next, we're going to try one of the other approaches to solving the recurrence for the Stirling numbers, namely that of studying the functions a and y. So a and y, so we just looked at b, k, x, so a and y, each time it's going to be summing over k. Y to the k. So once k is bigger than n, it's going to be 0. So this is going to be a finite polynomial. We could sum from k equals 0 to infinity or to n. But the way they're probably going to do it in the book is to sum over all integers. So we'll have to restrict to n greater than or equal to 1 if we're going to use the recurrence relation and playing around with this. This method is much harder to carry out to completion than the one we just used, but it turns out that these generating functions have other uses that are quite important from a theoretical point of view. Let's fix an n greater than 0. So let n be greater than or equal to 1. We take our recurrence relation, 1.6.3, multiply it through by y to the k. So it was n k, curly brackets, equals n minus 1, k minus 1, plus k, n minus 1 k. Multiply both sides by y to the k. And then sum over k. Well, I'm just going to be careful with my indices, and I'm going to sum from k equals 1 to infinity. K equals 1 to infinity, y to the k, n minus 1, k minus 1, plus, so this time, this k here, this coefficient, is going to be on the inside of our sum being summed over n minus 1, k, y to the k. Okay, now let's see what this leads to. So this bit here is just any minus the k equals 0 term. So I'm gonna define this being from 0 to infinity. But if n is greater than or equal to 1, then n choose 0 is just 0. So I'll write that in, I'll write minus n0 y to the 0, which is 1. What is this one here? Well, I'm going to take a y outside. So that this k's, the value here is the same as there, so yk n minus 1 k minus 1. Oops, it should be a y to the k minus 1. So when k goes from 1 to infinity, k minus 1 goes from 0 to infinity, so I might as well just change that to k and take k from 0 to infinity. And here we have this. This is going to be related to the derivative, isn't it? So what's this bit here? This one here is y times, oops, that should have been, no, that's right, so this is y times a n minus 1 y. So a n y, and if n is greater than or equal to 1, this is 0, it's equal to y a n minus 1 y plus this sum here, which we'll need to think about. So what do? They jump straight in with the derivatives. So let's work out what this would be. So we know what a n is, a and y is, so let's look at the derivative of a and y. So d by dy a and y equals sum from k equals 0 to infinity, n and k in curly brackets, k, y to the k minus 1. When k is 0, this term is 0 because we've got a factor of k there, so I'm going to take this as a sum from k equals 1 to infinity. Right. Now this is already looking similar to this, except we have an n minus 1 instead of an n, which is fine. We could just change that to an n minus 1. But here the power of y is k, and we've got a k there, but here we have a k minus 1 and a k there, so if we multiply through by y, then we get the sort of exact sort of thing that we're after, k y to the k. So this term here, so coming down here, we've got y a n minus 1 y plus y d by dy a n minus 1 y. Is this what they got? any equals y an minus 1y plus y times dy by dy an minus 1y. Okay. Then what have they've taken this factor of y. Okay. Sort of taking an minus 1y out. So let's see. So y 1 plus d by dy a n minus 1 y. Right. Yeah, I guess, I mean, it's just a way of writing it, isn't it? They've changed their d by dy to a big dy kind of operator, function operator. What is a 0y? So they say 1, so a 0y is just, well, so a and y was this, so a 0y, you get a 0 here all the time, so it's sum from k equals 0 to infinity, whoops, so a 0 is equal to 0k in curly brackets, y to the k, and the only time when this coefficient here is non-zero is when it's 0, 0, so it's just equal to 1 times y to the 0, so it's just 1. Okay, so yeah, so we have this formula, so a n y is equal to this, and a 0 y is a constant function 1. Okay, this is interesting. The novel feature is the appearance of the differentiation operator d by dy that was necessitated by the factor k in the recurrence relation. Hence, each function, an, is obtained from its predecessor by applying the operator y times 1 plus dy. So, yeah, sure, you can just think of that as being an operator. So if you think of 1 plus d by dy as an operator which is applied to functions that are in the variable y, so if you were to apply that to fy, it would just, what we mean by that is fy plus derivative d by dy fy. Beginning with a0 equals 1, we obtain successively y plus y squared, y plus 3y squared plus y cubed, and so on. But as far as an explicit formula is concerned, we find only that a n y is equal to y plus y dy to the power of n times 1, the function 1, by this approach. Okay, yeah, it does sound interesting. So I'm just going to check the first few terms, see how it pans out. So we have this, so a n y is equal to, it was y 1 plus d by, I'm just going to leave it like this, d by dy. They've been interchanging d by dy and big D subscript y, a n minus 1y. So the a 1y is equal to y 1 plus d by dy 1, which is a0, and so it's equal to y 1 plus d by dy 1, which is just 0. That's y. First one's y. So you get a0 y equals 1, a1 y equals y. So let's see. So just for future reference, d by dy of a1y is equal to 1. Okay, so a2y is equal to y 1 plus d by dy, a1y, which is just y, function y, which is y times y plus 1, which is y squared plus y. The derivative of this is 2y plus 1. So that is a2y derivative. Let's work out the next one. So this is agreed so far. This y plus y squared. Yep, and they've done the next one. So let's just do the next one and see if that's the same. So you're going to have a3y is equal to y. So a2y, which was y plus 1, and plus the derivative of that, which was 2y plus 1. Expand this out, so y squared plus y plus 2y plus 1, y squared plus 3y plus 1. Is that what they have? They have y cubed plus 3y squared plus y. Yeah. So, yeah. So we get this sequence of polynomials. There are, however, one or two things that can be seen more clearly from these generating functions than from the b and x's. One of those will be discussed in section 4.5 and concerns the shape of the sequence nk, curly brackets, for fixed n as k runs from 1 to n. It turns out that the sequence increases for a while and then it decreases. That is, it has just one maximum. Many combinatorial sequences are unimodal, like this one, but in some cases it can be very hard to prove such things. In this case, thanks to the formula 1.6.9 that we just calculated, we will see that it's not hard at all. Well, okay, that's cool. So, I mean, to me it's obvious that you're going to get this kind of hump, like I said, a kind of hump. So, you know, if you're looking at, say we're fixed n, and we're looking at k going in this direction, k, and we've got to say, you know, n is 20, then how many, so, you know, we've got this set from 1 to 20, so when k is 20, there is exactly one way to partition this into 20 classes, i.e. a class for each individual element, so there'd just be one here, and there's also exactly one way to partition it into one class, which is the entire thing. There's no ways to partition it into 0 classes, so yeah, I'm going to expect it to get big and then get large. I mean, I would expect this shape. I have no reason to, I suppose, think that it doesn't go up or down. It might have multiple points, but you know, you'd expect it to be something like this. But then on the other hand, it's not obvious that you got one maximum. Why not, you know, having two values here? It's not obvious that only one k we attain the maximum. Why not have two? Sort of like in binomial coefficients, you would have, say, two. You often get two maximums. So 3 choose 1 is equal to 3 choose 2. They're both 3. So it seems to be claiming that we have exactly one maximum, and there's a proof which comes from this, which is interesting. For an application of 1.6.7, 1.6.7 was the set of equations, seems to be the whole working out of what nk in curly brackets was from our function bkx's. So let's see. For an application of 1.6.7, recall that the Stirling numbers, nk, is the number of ways of partitioning a set of n elements into k classes. Suppose we don't particularly care how many classes there are, but we want to know the number of ways to partition a set of n elements. Let these numbers be bn, from 0 to, n goes from 0 to infinity. They are called the Bell numbers. It is conventional to take b0 as 1. The sequence of Bell numbers begins 1, 1, 2, 5, 15, 52, so on. Okay, I'm just going to check the first couple of these. I'm not going to try and calculate the whole sequence here. Let's just do a couple. So 0, so it's b0 is going to be equal to 1. It's the number of ways to partition the empty set. How many ways is there to write this as a union of disjoint non-empty subsets? Exactly 1. That is no disjoint non-empty subsets, so just one partition. The partition of empty classes. B1 is equal to, well, how many ways is there to partition 1? Well, we're going to need at least one class, and that has each class has a size of at least 1, so the only way to partition it is the whole set, the whole subset. So B2. Now we've got a few more choices. So how many ways to partition this? We could either have the whole set, 1, 2, or you could have it like this. So there's 2, and what's what? Maybe B3. You could do that quickly as well. So 1, 2, 3. You could have a whole set. You could split it into 2. So 1, 2, 3. And there's 3 ways to do it into 2. You could either have a 1 on its own, 2 on its own, or the 3 on its own. Or you could split it into 3. So 1, 2, 3. So you got 1, 2, 3, 4, 5. Does that agree for the first few? 1, 1, 2, 5. Yep, 15, 52, and so on. These are called the Bell numbers. Can we find an explicit formula for the Bell numbers? Nothing to it. In 1.6.7, we have an explicit formula for nk. If we sum that formula from k equals 1 to n, we will have an explicit formula for bn. However, there's one more thing that is quite profitable to notice. The formula 1.6.7, oh okay, 1.6.7 is a specific formula in here. It is referring to this particular line, so I'm just going to write that out. So nk curly brackets is equal to the sum from r as 1 to k, alpha r x to the n minus k of 1 over 1 minus rx. Right. So let's go back to where we were. I'm curious, is this 1.6.7 referring specifically to this line, or is it referring to the entire block of the entire equation block? Perhaps it's referring to the entire equation block, and what it means is the formula that we get at the end. So I'm going to write that out as well. nk curly brackets is equal to the sum r from 1 to k minus 1 to the k minus r to the n over r factorial k minus r factorial. I notice they say n and k is greater than or equal to 0. But so if k was 0, then we would have an empty sum here. We'd have an empty sum, and this would be 0. But if both n and k were 0, we would have an empty sum. Summing from r is 1 to 0. There's no terms in the sum, so it would be 0. However, 0 is 0 and curly brackets is 1, so it's valid for, I would suspect, n and k greater than or equal to 0, but n, k not equal to 0, 0. Okay, so what were they saying about this formula? So in 1.6.7 we have an explicit formula for nk. If we sum that formula over k from 1 to n, we will have an explicit formula for Bn. However, there's one more thing that's quite profitable to notice. The formula 1.6.7 is valid for all positive integer values of n and k. In particular, it is valid if k is greater than n. But then n, k in curly brackets is 0 if k is greater than n. This means that the formula 1.6.7 does not have to be told that 13, 19, the way to split a set of 13 elements into 19 classes is 0. It knows it. i.e. if we blissfully insert n equals 13 and k equals 19 into the Munster sum and work it all out, we will get 0. Hence, to calculate the Bell numbers, we can just sum the last member of 1.6.7 from k 1 to m, where m is any number you please that is greater than or equal to n. Let's do it. So, what do they mean there? So, Bn is the sum from k is equal to 0 to n of n choose k. However, yeah, like it says, we could choose anything bigger than n, because once k exceeds n, you always get 0 here. So if k equals 0, m, so m is greater than or equal to n, right? Is that what they've said? Yep. So we've got this formula here. So k equals 0 to m, and nk in curly brackets, using this formula I suspect. So sum from r equals 1 to k, minus 1 to k minus r to the n, over r factorial k minus r factorial. And then, what are we doing? They've taken, I've changed the order of the sum. Okay. So they've changed the order of the summation, which is fine. So essentially, we're summing from k from 0 to m and r from 1 to k. This is a rectangle, so it doesn't matter what order we sum it in, so I'm going to change the order from r from 1 to k. Oh, it does matter. It does matter, because r goes from 1 to k. It's not a rectangle. So what's going on here? They've changed the upper. So they've got the sum. You get the sum from r equals 1 to k, and then instead they've got a sum of r equals 1 to m. Right, and so if they're taking r from 1 to m, they've surely got to subtract a bit. Okay. So if I want to do this from r is 1 to m, let's see what this comes out. So k from 0 to m, r from 1 to m, which is going to be this bit, which is just, well, I'm just going to write it out, k minus r to the m over r factorial k minus r factorial. So when r is exceeding k, this is going to become factorial of a negative number, which can't do. So what's going on here? They're taking out, they're reordering it, so they're taking out r to the n minus 1 over r minus 1 factorial. So let's have a little think of this. So what did we have? So we've got that bn equals sum from k equals 1 to m, r equals 1 to k, minus 1 to k minus r to the n over r factorial k minus r factorial. So as k goes from 1 to n, r always goes from 1 to k. So so I just realised that this only works if n is non-zero, or if n is greater than 0, because here this was just substituting in our formula for nk in curly brackets. However, this formula fails when both n and k are 0. So if we plug in this formula in, we must assume that n is greater than or equal to 1. Don't think it mentioned that in the text. And if n is greater than or equal to 1 when k is 0, then k in curly brackets is 0. So might as well be taking the sum from k equals 1. So we're in line with what they've got in the book. So how might we go about rearranging this? They have something from r from 1 to m, and then there's something k from r to m. Why would they do that? K from r to m, it's weird. R is going from 1 to m. Just trying to understand how they've done this rearranging. Maybe if I just try writing out a grid and seeing how often r over the r to the n over r factorial is occurring for how many k's it occurs. So for what k does r equal to 1 crop up? Well, that occurs for all k. So when r is 1, when r equals 1 in this sum, k can be anything from 1 to n. So you'd have k goes from 1 to m, and r to the n over r factorial k minus r factorial. And when r is equal to 2, that only ever occurs for k greater than or equal to 2, because when k is 1, this sum never reaches 2. So you'd have plus r equal to 2. So this would be, you're also adding k going from 2 to m minus 1 to the k minus r to the n over r factorial k minus r factorial. I think I see where we're going now. So as r goes from 1 to m, so as r goes from 1 to m, r equals 1 to m, we can sum k from r to m. Yeah, I get it now. So if I'd just written this out as a grid, it should have been apparent that way as well. So Bn equals this, n greater than or equal to 1. Is this the same as what they've got? R from 1 to m, k from r to m, and then the same thing as normal, minus 1 to the k minus r to the n over r factorial over k. Yeah, it's the same thing. So the reason I've just sort of hand-wavingly explained why this works. Like, let's see if I can draw this out as a picture. So as k goes from 1 to m, so let's say I'm going to draw a picture. K goes this direction, 1, 2 to m. R goes this direction. So if we're looking at the sum, when k is 1, R goes from 1 to k. So 1, 2, R goes from 1 to m as well. So when k is 1, R, we only have a value for R is 1. So you have a value in the sum here. When k is 2, the sum goes from R equals 1 to 2. So there's a value in the sum here and here. When k is 3, the sum goes from, so you end up with this triangle. And when k is m, there's a value in the sum all the way up to rm. R is m. So you've got this triangle here. And for each coordinate in this grid, we're summing this equation for k and r equal to their values in this coordinate grid. So instead of calculating along the k, if we're calculating along the r, for when r is 1, you're summing k from 1 to m. When r is 2, you're summing k from 2 to m. So yeah, that's how they've been able to reorder this sum like this. It's just simple rearrangement of the sum. I should have just drawn the picture straight away and it would have been obvious. So we have Bn is sum from r equals 1 to m, k equals r to m, minus 1 to the k minus r to the n over r factorial k minus r factorial. They're working with r to the n minus 1 and r to the n minus 1 and r minus 1 factorial, but this is the same, it's just a little more compact to write, multiplying the top and bottom by r, it's the same thing. Since they've now rearranged, we can take the r's outside the sum over the k's, because r is constant, as k varies in this part, so r to the n over r factorial, k from r to m, minus 1 to the k minus r over k minus r factorial. And as k goes from r to m, k minus r is going from 0 to m minus r. So r to the n over r factorial. They're using a new variable, they're calling it s. S goes from 0 to m minus r. So s is replacing k minus r here. Minus 1 to the s over s factorial. Okay, so now we've got it in the form that they have. But now the number m is arbitrary, except that m is greater than or equal to n. Since the partial sum of the exponential series in the curly braces above is so inviting, yes, let's keep n and r fixed and let m go to infinity. This, okay, this is sounding cool. This gives the following remarkable formula for the Bell numbers. Check it yourself for n equal to 1. So let's say, so as m goes to infinity, well, if m if m is infinity, then this is, yeah, if you know the well-known power series of e to the x, so it goes from, say, n equals 0 to infinity, x to the n over n factorial. You see that if this was infinity here, this bit here would just be e to the minus 1 equals 1 over e. So if we were to take m as infinity, it does seem a bit unrigorous. Then you're gonna have r equals 1 to infinity, r to the n over r factorial, s from 0 to infinity minus 1 to the s over s factorial equals the sum from r equals 1 to infinity r to the n over r factorial, and then this bit is e to the minus 1, so I'll put 1 over e outside here. So, but the reason it isn't rigorous is because we haven't proved something in this here. So what we haven't proved, so we know that for all m greater than or equal to n, bn is equal to the sum from r equals 1 to infinity r to the n over r factorial, s equals 0 to n minus r minus 1 to the s over s factorial. We know that this is true. So this value does not vary as m increases if m is greater than n. So we know that lim as n goes to infinity of this thing here, r equals 1 to the m r to the n over r factorial, plugging it all back in, we know that this limit has to be equal to bn, because this is a sequence, and once m is bigger than n, it's always the same value, it's always bn, it never varies. So this limit exists and it has to be equal to bn. But what we don't know is that this limit is equal to this, just plugging in infinity. It's a different matter. It's a slightly different deal, because you've got two sums going on here, so it's not so straightforward. So this is not a proof that the Bell numbers bn are equal to this. However, it's not a proof that bn is equal to this. However, it does look inviting, as it says. It says it looks very inviting. Let's keep reading. I say check it yourself at n equals to 1. Right, well, if n is 1 in this formula, then you've got 1 over e, r equals 1 to infinity, r to the n, so it's just r over r factorial. Okay, this is 1 over e, r equals 1 to infinity, 1 over r minus 1 factorial. And as r goes from 1 to infinity, r minus 1 goes from 0 to infinity, so this is 1 over e, r equals 0 to infinity, 1 over r factorial. And again, as I say, from the well-known power series in the exponential function e to the x, this is 1 over e times e, which is just 1. Okay. It's a really cool formula though. Perhaps it can be proved by induction, if this is our base case. Perhaps we can prove that, so that would mean, we know that b1 is equal to this formula for when n is 1. So maybe we could show that this has to satisfy the occurrence relation that we've got. So let's see. This formula for the Bell numbers, although it has a certain charm, does not lend itself to computation. From it, however, we can derive a generating function for the Bell numbers that is unexpectedly simple and elegant. We will look at the generating function in the form bx is the sum n greater than or equal to 0 of bn over n factorial x to the n. Okay. So we're using our Bell numbers as our, when dividing them by n factorial, as our coefficients in power series. This is the first time we have found it necessary to introduce an extra factor of 1 over n factorial into the coefficients of a generating function. This kind of thing happens frequently, however, and we will discuss in chapter 2 how to recognise when extra factors like this will be useful. A generating function of the form 1.6.11, where the 1 over n factorials thrown into the coefficients, with the 1 over n factorials thrown into the coefficients, is called an exponential generating function. We would say, for instance, that bx is the exponential generating function of the Bell numbers. When we wish to distinguish the various kinds of generating functions, we may use the phrase the ordinary power series generating function of the sequence an is the sum an x to the n, or the exponential generating function of the sequence an is sum an x to the n over n factorial. Okay. To find bx explicitly, we take the formula 1.6.10, which is valid for all n greater than or equal to 1, multiply it through by x to the n over n factorial, and sum over all n greater than what? Greater than or equal to 1. Okay, so let's try that. See if that's easy to do. So the big bx is equal to sum from n equals 0 to infinity bn over n factorial x to the n. And we have this formula which I'm not happy, which we haven't proved. But let's just take their word for it for the time being that it's correct. R goes from 1 to infinity, r to the n over, was it r1 to infinity or 0 to infinity? It was 1, wasn't it? No, it was 0. Okay. It's from 0 to infinity. They're saying that when r is 0, this term is 0. Okay. So it doesn't make a difference. So multiplying this by x to the n over n factorial bn equals 1 over e x to the n over n factorial sum r from 0 to infinity r to the n over r factorial, and then we're going to sum over n is 1 to infinity x to the n over n factorial bn, which is bx minus the n equals 0 term. And so this is equal to 1 over e n equals 1 to infinity x to the n over n factorial sum r equals 0 to infinity r to the n over r factorial. b0 was 1, 0 factorial was 1, so this is just bx minus 1. So what do they have? They have bx minus 1 is 1 over e, sum n from 1 to infinity, x to the n over n factorial, sum from r is, well, 1 to infinity. Yeah, it's the same thing, right? And then what they've done next. Now, yeah, okay, they've reordered the sum, and that's fine this time because we don't have the top index depending on the other variable that's being summed over. So yeah, we can just reorder the sum. So it's 1 over e r equals 0 to infinity, n equals 1 to infinity. So that means we can take the r factor out before this sum. Okay, and so this bit here is e to the x, isn't it? Well, it's e to the x minus 1, I think, because we're only summing from n equals 1, not n equals 0. So this is 1 over e, r equals 0 to infinity, r to the n over r factorial, e to the x minus 1. Right. And do they have that? Ooh, no. Perhaps I made a mistake. Well, no, I didn't. However, they left this Rn inside here, and he only took out the 1 over r factorial, which is fine. We don't have to take it out, and so then this becomes 1 over r factorial e to the rx, so it's e to the rx minus 1. Yep, that's what they've got. And then what do they get with this? So, they split this into two sums. So it's first the sum from r to infinity of 1 over r factorial e to the rx minus sum from r equals 0 to infinity of 1 over r factorial. Okay, and this bit here is e, and what's this bit here? Well, we can think of this of e to the x to the power of r. So write that as e to the x to the power of r. You see that this is just e to the x. So yeah, so it's 1 over e to the e to the x minus e. Yeah, and that's what they've got, and they've taken this e, factor of e out. So e to the x minus 1 minus 1. So we have therefore shown theorem 1.6.1. The exponential generating function of the Bell numbers is e to the x minus 1. Yeah, so because this was b x minus 1, therefore bx is e to the x minus 1, i.e. the coefficient of x to the n over n factorial in the power series expansion of e to the x minus 1 is the number of partitions of a set of n elements. Okay, well, I don't think we have shown that because there's some issues there, isn't there? There's the issue that I wasn't quite convinced that we can do what we claim to do with the formula for Bn. It still needs some work to show that that's true. And there is also some manipulations, algebraic manipulating in here, which needs a little bit of care. Because you've taken this sum here, and then we are splitting it into two, so you need to show that you can do that. But it looks like it should be fairly easy to show that you've got absolute convergence of this part and absolute convergence of that part, I think. So that should be okay. Yeah, like both this side and this side should converge on their own. Yeah, but in particular to those values, so that shouldn't be too much of an issue. But yeah, so the only issue was this formula here for Bn. And as I mentioned earlier, I'm a little bit skeptical. Well, I'm not skeptical of the fact. I'm sure it's a true fact. But I'm skeptical that there isn't more involved in showing that this is true. Let's read a bit more. So, this result is surely an outstanding example of the power of the generating function approach. The Bell numbers themselves are complicated, but the generating function is simple and easy to remember. The next novel element of this story is the fact that we can go from generating functions to recurrence formulas. Although, in all of our examples to date, the motion has been in the other direction. We propose now to derive from theorem 1.6.1 a recurrence relation for the Bell numbers, one that will make it look easy to compute as many of them as we might wish to look at. First, the theorem tells us that, so this is a function bx, sum from n equals 0, big Bx, sum from n equals 0 to infinity of little bn over n factorial x to the n is e to the x minus 1. We are going to carry out a very standard operation on this equation, but the first time this operation appears, it seems to be anything but standard. So, the x d by dx log operation. Well, this looks like a fairly substantial little section of this section 1.6, so I think I'm going to stop there, as this video has already gone on fairly long. I am going to have a little think about the formula for little bn, the Bell numbers, in terms of the exponential function and the infinite sum. I'm going to have a little think about that and see if I can come up with a proof that it is in fact equal to that formula. Because just saying, taking m to infinity, you with analysis you need to be really careful with that sort of thing. So I'll have a little think about that and talk about it next time. So that's it for now. Thank you for watching. See you again next time.